In this section, we're going to look at adding and subtracting polynomials. And before we do that, I should probably tell you what those things are. So let me start with a definition. A term is an expression of the form ax to the n, so that's a times x to the n. A is a number. And x is a variable. So just as an example of things like this, we're going to have, I don't know, 5x squared. That's considered a term. Negative 3x cubed. You can see that each of these have a number of times x to a power. 10x, that's a term. Negative 400, x to the 20. All these are examples of terms. Even something like this. The number 5 is considered a term because you could think of 5 as being like 5x to the 0 power because x to the 0 is equal to 1. So all of these things are considered terms. Then we come to a polynomial. Is an expression involving sums and differences of terms. And I think up here, when I did the definition of a term, I also should have said that n is a whole number. So n is a positive integer, or it's 0 is allowed. That's allowed for a whole number. So that's why all of these things are considered terms, because the powers on x are all whole numbers. When they don't write anything, that's to the 1 power. You got to the 20th power. You got to the 0 power. All those things are terms. Polynomials are just a sum or difference or combination thereof of those things. So examples of polynomials are like this. 3x squared minus 2x plus 1. That's an example of a polynomial. Negative 4x to the 5th minus x. That's an example of a polynomial. 7x cubed plus x minus 9. So all these are examples of polynomials. Look at the terms that you have here. The terms in this one here are 3x squared, negative 2x, and 1. Notice that the power on x is 2, then 1, and then when that's the constant part, or just the number part, that's like x to the 0. So you can see all the powers are correct. So that last polynomial, consider 7x cubed plus x minus 9. The terms of that polynomial are 7x cubed, there's one term, x, there's another term, and negative 9. The negative or positive is attached to the term, so keep that in mind. While we're at it, let me do some other definitions. The numbers in each term are called coefficients. I think I want to be a little more, just saying the numbers that are in each term is not such a great, not exactly the best way of saying it. Let's put it this way. In front of x, those are the things I'm talking about. So when we look at 7x to the third has 7 for a coefficient. X has 1 for a coefficient. And while I'm here, the last part of it, the -9, is called the constant term. The degree of a polynomial is the highest power of the variable. So, as an example, 7x cubed minus 3x plus 4 has degree 3. Negative 2x minus 5 has degree 1. The highest power that you see for x here is equal to 1. Let's see some other ones here. Negative 4x plus 7x cubed minus 9x to the 5th has degree 5. And so on. You get the idea, I hope, by now. You see that the highest power of x is always going to be the degree, or whatever the variable is, it's just the highest power. Now, multivariable polynomials can look like this: 2x squared y minus 4xy squared plus y to the 5th minus x to the 9th y to the 3rd. Stuff like this. This is a polynomial. But telling the degree of this is different. The terms. The terms are, we have 2x squared y. There's one term. Then we have negative 4xy squared. There's another term. Y to the 5th. There's another term. Negative x to the 9th, y to the 3rd. Now, the degree of this polynomial, it's a little bit different than what I described before. The definition I gave before was for a single variable polynomial. This has multiple variables. What you do in situations like this is you look at the exponents on the x and the y, and if they're multiplied together, you add them. So, for example, the degree of x squared y is actually equal to 3. The degree of xy squared is equal to 3. That's because the 1 from the x and the 2 from the y, they add together to give you 3. The degree of this piece here is 5, and the degree of this piece here is 12. So the degree of this polynomial is the highest power that I can get through adding or single or by itself like that is this 9 plus 3 is 12. So remember that when you have polynomials like, I don't know, let me do another example. 5a cubed b squared minus 2ab cubed plus 3b cubed minus 2ab, something like that. If I go through here, let me go ahead and tell you the degree here of that piece is 3 plus 2 equal to 5. For this piece here, the degree on that one is 1 plus 3 equals 4. This one speaks by itself. The degree is 3. And then this last one here, the degree is 1 plus 1 equals 2. Now if I look through all of these here, the highest power, or sum of powers, I guess, when you have multiple variables, is 5. So the degree equals 5. Not only that, let me separate it from the last problem. Not only that, the coefficients. 5 is the coefficient of this first piece. -2 is the coefficient of the next piece. +3, and then -2. So the numbers that are attached to the variables out front are considered the coefficients. Hopefully this is enough for you to tell what the degree of a polynomial is when you're given one. Let me do another example here. If I have something like 7r to the 3/2 plus 9r minus 4, an expression like that is not a polynomial. Why? Because one of the powers is not a whole number. Right here, 3/2 is not a whole number. So one of the powers, 3/2, is not a whole number. Now, if something like this, though, 7r to the 3rd plus 9r minus 4, well, that's easy. That has degree 3. So the problem with that expression that we had in this example here was that exponent. So we're not going to be dealing with anything that has exponents that are not whole numbers. So that should give you a little bit of a sigh of relief, because once you start dealing with fractional exponents, things like that, things get very complicated. Now next we have these definitions. Monomial. This here is an expression with only one term. So, as an example of this, we could have 2x cubed. That would be an example of one. -4xy to the 5th. That would be another example of a monomial. Just a single number. That's an example of a monomial. X cubed y to the 5th. All of these are examples of monomials because they consist of a single term. We don't use a lot of industriousness when we come with definitions, as you'll see on the next one. Guess what a binomial is? That's an expression with two terms. So examples of binomials are like x plus y, 3x squared minus 9, 4x to the 9th y cubed minus 2xy squared. That's another example of a binomial. I think you get the idea. 27x minus x cubed. All of these things are binomials. I should put these are examples of them. And then we all the way up to trinomial. And I'll bet you can't guess this one either. An expression with 3 terms. So, I don't know, let's see, we could do x squared plus x plus 1. This would be an example of these things. 2x minus y plus 4. X squared y squared minus xy squared plus xy. All of these have 3 terms, so they're called trinomials. Nothing really complicated about any of that, I hope. And so let's do a little bit of the definitions, a little practice with that first. So here's an example. I have ax squared plus bx plus c, and the number a does not equal 0. That means, so the x squared is actually there. If a was 0, the x squared, well, wouldn't be there. So this is degree 2. It's a trinomial because it's got 3 terms, and the coefficients are a, b, and c. In fact, I made a slight mistake there. The coefficients are actually the numbers attached to x. C is called the constant term. So I should be careful about that. Coefficients are only attached to powers of x, non-zero powers of x, actually. So let's continue on here. As another example, I have 6a squared plus 2a minus 11. Let's see, we have our terms. We have 6a squared. That term is of degree 2. Then we have 2a. That term is of degree 1. The power on a there is just 1. And then negative 11 is the constant term. And so we've seen them have more than one variable, something like this. We have 3c squared d squared plus 0.7 c squared d plus cd minus 1. Here are the terms. Let me write those down. We have 3c squared d squared. This term right here, the degree, equals, now what you have to do with those powers is add them together. So it's actually 2 plus 2, which equals 4, because there's a 2 as a power for c and a 2 for the power of d. Then we have 0.7 c squared d. That has degree 2 for the c plus 1 for the d, gives us a total degree of 3 for that part. CD, the degree here, the power on both c and d is 1, so that's 1 plus 1 equals 2. And then finally, negative 1 is the constant term. All right, now let's move on to some computational stuff. Most of this is just definition stuff. I'm not really too keen on it, but we've got to lay down those rules so that I know how to use what words I can use going forward. Now, sometimes what we're going to be doing with these things is replacing the variable with a number. So, for example, look at this thing, evaluate, and I have 2r cubed plus 5r minus 6 for A, r equals 3, and part B, r equals negative 1. So let's go ahead and solve this. I'll do part A first. That's when r is equal to 3. So what we're going to do is replace r by 3. And was that to the third power? So look here, the assumption, the natural assumption here is that between the 2 and the r you have multiplication going on. That's why I put the dot here, because if I didn't it would look like 23 to the third power. But then I need to replace the r after 5 as well, so I'll put a 3 there, and then minus 6. And then when I evaluate this thing, I'll get 2 times 27 plus 5 times 3 minus 6. Now I'll do the multiplications. 54 plus 15 minus 6, and that will give us 63. For part B, r equals negative 1. I highly advise you, when plugging a negative number in for the variable, to plug it in with parentheses around it. You'll know how to work it better if you do that. And let's see what we get then. Well, negative 1 to the third is just negative 1. So I have 2 times negative 1, and I have plus 5 times negative 1 minus 6. 2 times negative 1 is negative 2, and I have minus 5 minus 6, and that's a total of minus 13. Let's do a couple more examples. Evaluate. Here we have negative 2xy squared plus 7xy plus 12y minus 6 for x equals 5, y equals negative 2. So here I have two variables to plug in for both x and y. So watch what I do. Since the y has a negative, I'll put it in parentheses. So this is what I'm going to get. Negative 2. The x was 5, so I don't have a problem putting it like that. But now the y was negative 2, so I'll put negative 2 in parentheses and square it. Plus 7 times 5 times negative 2. Plus 12 times negative 2 minus 6. Now, from here on out, it's just the order of operations that you're going to be using. For instance, the highest order of operation in this whole problem right now is the exponent. So I get negative 2 times 5. Negative 2, when you square it, is positive 4. So I'll put a dot 4 for that piece. Now, I'm not going to perform any other operations just yet because they were all lower. I'll just copy everything down. Now I'm ready to do my multiplications. And I'm not going to do them in a slow fashion. I'm just going to do them all at once. So for example, this 2 times 5 is 10 times 4 is 40. So I'll get a negative 40 for that piece. For this piece here, 35 times negative 2 is negative 70. Then I get negative 24. And then I get minus 6. And I'll just go straight across. Negative 40 minus 70 is negative 110. Minus 24 is negative 134. Minus 6 is negative 140. Evaluate x squared minus y squared for x equals 5, y equals negative 5. And this is crucial now to put parentheses around the negative 5 when you put it in. I'll get 5 squared, there's the x squared part, minus, and then I'll have negative 5 for the y and square it. Now I'll do my work underneath of it. 5 squared is 25. Bring down the minus. Negative 5 when you square it is also positive 25. And 25 minus 25 is 0. Example. Everybody remembers the old joke about Newton discovering gravity because an apple hit him on the head. Well, let me give you an example of such a situation like that. It was Newton that did discover the rules of gravitation, but I'm not so sure he did it because an apple hit him on the head. But nonetheless, suppose you drop an apple from 1,000 feet above ground. The formula for the height of that apple this formula only works after the apple is released. The formula is given by this. H equals negative 16t squared plus 1,000. This is a formula for how high the apple will be at any time. Oh, t is measured in seconds. So what I want to do then is how high is the apple after 5 seconds? So the solution to this is I'm going to replace t with 5. So my h equals negative 16 times 5 squared plus 1,000. Now the answer will be in feet. This height is listed in feet. So I get negative 16 times 25 plus 1,000. Negative 16 times 25 is negative 400. So my answer then is 600 feet in the air still. So this gives us an introduction to polynomials and exactly what they do. Their uses are far and wide, but we need to learn how to do simple things with them first before we do anything more complicated. So we're going to talk about adding and subtracting them. So I think probably I've got one phrase, and this describes the whole process. Combine like terms. Believe me, we'll do enough examples to where you'll understand what I'm talking about. That's the key phrase that we're going to be going here when adding and subtracting these things. I'll show you what I mean. We've done stuff like this before. This is not the first time we've ever combined like terms. Here's an example of something that you'll see. The instructions just say to add. And what I have is negative 4y cubed plus 3y to the 5th plus 17y to the 5th plus 6y cubed minus 5y to the fifth. Now, when you're writing your answers and things like that, the order that you write them is not important. However, when I do my examples, I'm always going to have it written so that the powers of the variable will go from higher to lower. You'll see in this example what I'm talking about. What I'm going to do is move stuff around so that all the like terms are by each other. So what I did is I saw that I had a 3y to the fifth, a 17y to the fifth, and a negative 5y to the fifth. Those are all like terms. I moved them together. Then the other like terms that I have is negative 4y cubed and 6y cubed. So I'll have minus 4y cubed plus 6y cubed. Remember, the commutative property allows you to move these things around like this. Now, like terms was important because then for these three terms right here, all the ones with the y to the fifth, I can factor out a y to the fifth, or if you will, distribute out a y to the fifth from those three terms. And I can also do something like that for the second two terms. I can factor out or distribute out a y to the third, like so. Notice that I put a plus here so that when all is said and done, my sign will be correct if I need it. Alright, here let's add these numbers up. I get 20 minus 5 is 15, so I get 15y to the fifth. And then here, negative 4 plus 6 is positive 2, so I'll get plus 2y to the third. So you can see, combining like terms was exactly what I did to add that stuff together. Let's do some more examples. This one I have 5/4 w to the third plus 3/8 w to the fourth minus 2/3 w to the fourth minus 5/6 w to the third. So what I'm going to do is probably put all my w to the fourths first. So I will have 3/8 w to the fourth minus 2/3 w to the fourth. And then I'll put the to the third powers after that. As I mentioned, it's just me that does this, where I put the powers from highest to lowest. You're not bounded by that unless your instructor tells you you have to. So now I've got my w to the fourth and my w to the thirds, I guess, partitioned. And so now let me go and look at my coefficients that are attached to the w to the fourth. That would be the 3/8 and the negative 2/3. So whatever that coefficient turns out to be, that'll be the thing in front of w to the fourth. And then in front of w to the third, I'll have 5/4 minus 5/6. Alright, in order to do any of these fractions, I need common denominators. For this piece right here, my common denominator will be 24. So 3/8, if I rewrote it over 24, would be 9 over 24. And then the 2/3, if I wrote it over 24, would be 16 over 24. Now for these, the LCD of 5/4 and 5/6 is 12. So I'm going to rewrite the 5/4 over 12. That would be 15 over 12. And the 5/6 instead over 12 would be 10 over 12. And that's attached to w to the third. Now I'm ready to go. 9 minus 16 is negative 7, so I get negative 7 over 24 w to the fourth. I dropped the parentheses, they're no longer needed. plus the 15/12 minus 10/12 is 5/12. W to the third. And hopefully this is not too big of a deal. You just move them around, get the terms that are like each other. By now you should be able to tell like terms pretty much by looking at them. My next one, I have x to the fifth y squared minus 14xy plus 6xy plus 5x to the fifth y squared plus 8xy. So when I look at this across from this, little test for you, while if you're paying attention, the degree of this polynomial is 7, because the 5 plus 2 does add up to be 7. Anyways, what I'm going to do is put my x to the fifth y squared terms together. So I had an x to the fifth y squared plus a 5x to the fifth y squared. As you use them up, this is something that I do. I kind of just mark them off so that I know that I've used them. And then I have all the stuff that was attached to xy. And so let me go ahead and write those next. So I got negative 14xy plus 6xy plus 8xy. Now, I'm going to put a 1 in front of this just to make it evident. I'm not going to do as much detail as I did before. Basically, when you do the distributive property up here, it's allowing you just to focus on the coefficients. So if you look, I have 1 of this thing plus 5 more of that same thing for a total of 6 of them. And you can do the same thing for the xy's. I got negative 14 of them, plus 6 puts me at negative 8, plus 8 puts me at 0. So there's no xy terms. All you end up with is this. Once again, we're going to add, so I'll have m squared minus 3m minus 8 plus 2m squared plus 7m plus 1. What I'm going to do here is a little bit different than the previous problems. There's another way that you can add, and it looks like this. I can do, some students like this, so I think I'll include it. Plus, they can go and stack them like I'm doing, but put your like terms underneath of each other, and then you can add these just like you would numbers, you know, column by column. So for example, negative 8 plus 1 is equal to negative 7. And then negative 3m plus 7m is equal to 4m. Put a plus because I'm creating a polynomial. And then finally, 1m squared, if you don't remember, there's a 1 in front of there. 1m squared plus 2m squared is 3m squared. And there you go. So there's another way of doing it. You might find it helpful as far as keeping track of all the terms if you stack them up like that. So let's do a couple of examples with this kind of addition. Here, let's add. I have negative 1.7p to the third minus 2p squared plus 3.8p minus 6, and I'm adding to it 6.2p cubed minus 1.2p plus 14. And let's see what all we have. Well, the good thing about these polynomials is you don't have to worry about carryover. There's no such thing of it in these things. So I just go by column and column, and whatever number I get, I get. So negative 6 plus 14 gives me an 8. And then 3.8 minus 1.2 is 2.6. So that'll give me a 2.6p in that spot. There's nothing. This is like a 0. This gap is like a 0 here, so I'll just bring down the negative 2p squared. This was a positive 2.6, so let me put a plus there. And then finally, negative 1.7 plus 6.2 is 4.5. And there you go. Another one. 7/4 y cubed minus 3/8 plus 5/6 y cubed plus 7/6 y squared minus 9/16. And so if I decide to use this stacking method like the previous problems, here's what I'll have. I'll have 7/4 y cubed. And then what I'm going to try to do is, since I have a y squared in this second piece, I don't have one here. I'm going to leave a gap, and I'll put negative 3/8 so that I don't mess up my like terms. I'm going to add to that. I got a 5/6 y cubed that I can put under there. But then I have plus 7/6 y squared, and then nothing more. Oh, sorry, minus 9/16. So I can do all these things then. Now, when I add these, I'm going to get something here. In the middle, though, all I have to do is drop that piece down. So I'm going to drop down the 7/6 y squared. And the rest of these, I got to get common denominators to do. So if I want to do 7/4 plus 5/6, I have to write it as a fraction over 12. So I get 21/12 plus 10/12 will equal 31/12. So I'll get 31/12 y to the third. These both have the same sign, so I'm adding. So I'll set these over to the side. So I'll have 3/8 plus 9/16 is the same as 6/16 plus 9/16, which is 15/16. So I get minus 15/16. There's nothing essentially complicated about dealing with fractions, except they do make things, I should say nothing harder about dealing with fractions, but they are more complicated. Now, subtraction shouldn't surprise you much at all. Let's do an example here. So I want to subtract, and what do we get? Negative 7d squared plus 15d plus 6 minus 8d squared plus 3d minus 9. Now, the parentheses in front of the first part are really not necessary, but I guess it's to show that we have a polynomial minus a polynomial. So I'll get negative 7d squared plus 15d plus 6. But don't forget, this negative is like a negative 1 in front of this second part. So you're going to distribute the negative all the way through to all three parts. So this negative 1, you're going to have to distribute to all three parts. And you get negative 8d squared, and then I have negative 3d, and then I have plus 9. So you can go ahead and work these if you want in the same fashion that I did before. Negative 7d squared plus 15d plus 6. And then what I'm going to add to this, because the minus signs have already been accounted for, I have negative 8d squared minus 3d plus 9. The negative 7 and the negative 8 gives me a negative 15d squared. 15 minus 3 gives me 12. Then I have a d plus 15. So now let's focus a little bit on subtracting. The same instruction each time, subtract. And this time we have negative 5d to the fourth minus 8d squared plus d plus 3 minus negative 3d to the fourth plus 17d cubed minus 6d squared minus 20. And when you actually do this in the last one, I think I did do I showed the distributive, so don't forget to apply this negative to all four parts of the second polynomial. So that'll give me negative 5d to the fourth. What I'm going to do is stack them like I did before. But what I noticed is that I have no d cubed term, but I have a d cubed term here. So I'm going to leave a gap. I'll get negative 8d squared plus d plus 3. This is why going from highest to lowest is very useful sometimes. Now when I apply the negative to this piece here, I'll get a positive 3d to the fourth. Then I'll get a negative 17d cubed. So that's going to fill in that spot right there. Then I get a positive 6d squared. And I don't have a d term, so I'm going to have a gap down here as well. But I do have a positive 20. So this is very useful, this technique, for lining up the like terms. So when I do the d to the fourth, I'll get negative 2d to the fourth. Bring down negative 17d cubed minus 2d squared plus d plus 23. Continuing on, here's a little more cumbersome example. We have 3r plus 2 minus r squared plus 5r minus 1 minus negative 9 r cubed minus r plus 6. So now when I throw my negatives through, I'll get 3r plus 2 minus r squared minus 5r plus 1. I distributed the negative. Plus 9r cubed plus r minus 6. And I noticed that my powers, I have everything from no power to 1 power to 2 power to 3 power. So the power is what I'm going to organize it by. So I'm going to take and put, let's see here, I think I'm going to just move all the terms closer together. So I got a 9r cubed. So I'll slice that one since I've made use of it. I don't see any r squareds except that single negative r squared that was right there. Then the r's, I have a 3r, a negative 5r, and a positive r. So I have plus 3r, negative 5r, plus 1r. So let me slice those off since I've used those up. And then my numbers, I have a 2, a 1, and a negative 6. So that gives us 9r cubed minus r squared. And now for just the r's, 3 minus 5 is negative 2, plus 1 more is negative 1. So I have negative 1r. And then to finish it off, 2 plus 1 minus 6 is negative 3. Let's try a more complicated example. Next we have 3/5 c to the fourth plus c cubed minus 3/2 c squared plus 1 plus c to the fourth minus 6c cubed minus 1/4 c squared plus 6c minus 1. So if I want to do it adding like terms together, stacking them up like two rows, I'll have 3/5 c to the fourth, and underneath of that I'll have just a 1 c to the fourth, so I'm adding these. I have a plus c cubed, and then I have a negative 6c cubed. Then I have a negative 3/2 c squared. So where I'm getting these top ones are coming from here. I'm just copying these down. But I'm also looking here to see if I have a matching power. So like the negative 1/4 c squared I'll put underneath of here. And then I don't have a c term, but I have a c term here. So I'll leave a gap. Let me put a plus 6c here. And then I'll put, I have a plus 1 in the first polynomial and a minus 1 in the second polynomial. So let me go ahead and add up all of these things. 1 minus 1 is 0, they cancel. 6c will remain, of course. Now 3/2 minus 1/4, or negative 3/2 minus 1/4. I have to do 3/2 plus 1/4. I am going to leave it to you, because 3/2 to me is like 6/4. I'll write this as negative 7/4 c squared. 1 minus 6 is an easy one, so I get minus 5c cubed. And then finally, there's a 1 in front of the c to the fourth. 1 plus 3/5 is equal to 8/5. I'm thinking of 1 is equal to 5 over 5. Let's see how complicated we can make this stuff. Next one, we're going to have j squared minus 13j minus 9, and I'm going to subtract from that negative 7j squared plus 10j minus 2 plus 4j squared minus 11j minus 6. So in each time I plan to show you a little bit more than what I did before. So and the idea is to give you some efficiency. I have to do these brackets first. There's no need for parentheses around this first polynomial. So it can just be j squared minus 13j minus 9. Then for the second piece, if I look at the j squared pieces, negative 7 plus 4 gives me a negative 3j squared. So you can slice those off if they seem to be in your way. Next, if I look at just the j's, I have positive 10j minus 11j. That leaves me with negative 1j. All right. And then finally, the negative 2 and the negative 6 together give you negative 8. Now I'm going to distribute the negative through. So I get j squared minus 13j minus 9. As it goes through, I'll get plus 3j squared plus j plus 8. So all those things have negative values in front of them. Then I can move this around. I'll get my j squared plus 3j squared, negative 13j plus j, minus 9 plus 8. I'm not telling you that you can't do the stacking method where you line them up in this example. Just for me, it seemed a little bit easier to go straight across like this. So my j cubed, I'm going to get 1 plus 3 will be 4j squared. Then I'm going to get negative 13j plus 1j. That'll be negative 12j. And then finally, negative 9 plus 8 will be negative 1.